In example 8.3, we had a uniform mass of 12 kilograms, the Planck, and the Planck's mass, we assumed that its center of gravity was right at the center of the Planck, and that gave us an idea of how to establish where the force was applied and where the torque was applied. Most bodies, though, are not uniform, and in example 8.5, we're going to use some techniques of where we have measured forces to determine where the center of gravity of a non-uniform body is. In this example, we show how to find the location of a person's center of gravity. Suppose your lab partner has a height L of 173 centimeters and a weight of 715 newtons. You can determine the position of his center of gravity by having him stretch out on a uniform board supported at one end by a scale as shown in figure 8.12. If the board's weight is 49 newtons and the scale reading is 350 newtons, find the distance of your lab partner's center of gravity from the left end of the board. All right, so we've got a fulcrum over here, and we'll I'm not sure if that's the best place for the fulcrum. Actually, we should decide where to put the fulcrum kind of after we draw the forces. The force of the scale is 350 newtons. The weight of the board is 49 newtons. The weight of the person is 715 newtons, and we don't know exactly where that's going to be. Let's put it here. 715 newtons. So we've got the length, the weight of the person, the weight of the board, the force of the scale. So we got the three forces, and we need the x center of gravity. Okay, so if we use this as our zero, then this whole distance is 1.73 meters. And we're supposed to assume that the board is exactly the same height as the person. So this will be 1.73 over 2 to where the mass of the board, the uniform board, we're assuming the board has a uniform mass. And so we'll do sum of torques equals sum of the counterclockwise minus the sum of the clockwise equals 0. The counterclockwise torques include the 350 newtons times 1.73. That would be this right here. And the clockwise would include the 49 newtons at 1.73 over 2 and the 715 newtons at an unknown distance x center of gravity. And that is going to be all equal to 0. So solving that, the balance, or the weight measuring device, gives a torque of 605.5 newton meters. The board gives a torque of 42.4 newton meters, and the person himself will be providing a torque of 715 times his position. Solving for x sub cg, x center of gravity, we get 78.787 meters or 78.7 centimeters. And the given information is sufficient only to determine the x-coordinate of the center of gravity. So the height above his feet or below the top of his head. The other two coordinates can be estimated based on the body symmetry. Question 8.5. What would happen if a support is placed exactly at x equals 79 centimeters, followed by the removal of the supports at the subject's head and feet? So with 79 centimeters, and you put a support right there, and where is that? It's about 46% of the way from his head to his toes. So assuming that calculation is correct and the support is robust enough, if it's sizable enough, then he should be able to balance on that point. If it's a needle, or if it's got a pinprick on the top like this thing does, then he'll probably start to slowly uh, rotate one direction or another because of the rounding errors. Question exercise 8.5. Suppose a 416 kilogram alligator with a length of 3.5 meters is stretched out on a board of the same length weighing 65 newtons. If the board is supported on the ends, as in figure 8.12, and the scale reads 1880 newtons, find the x component of the alligator's center of gravity. So the torques acting on the board causing it to rotate include the unknown force of the fulcrum pushing upward, so that is a zero torque. The downward, or the clockwise torque of 416 at x sub g, so that's minus 416 x sub g, counter or clockwise, and then 65 newton, the board itself, 65 newtons at 1.75 minus 65 times 1.75, and then counterclockwise, the 1880 at 3.5 that is being measured by the scale. So plus 1880 times 3.5. Except I want the weight of the alligator, not its mass, so let's change that to 416g. And we get a distance of 1.59 meters for the distance from that point to the center of mass. .59.